Good afternoon, students. So let us continue from where we left last time. We were doing the electric charges and fields chapter, right? So let's continue with that. So this is what we did last time. If you remember, we found out the expression for electric field. We did the derivation in the last class, and your electric field comes out to be this, right? K x q naught divided by x square plus a square, and the electric field was in this direction. Right? So total charge on the entire ring is q naught. On the axis, electric field is only electric field on the axis. The electric field is only along the axis, right? Not perpendicular to it, right? And how much is the electric field? The value is given by that equation, and we had derived it in the last class, right? So I hope that part is clear to everybody. Now, now let us listen to something very interesting. I'll get that formula here again. E vector is equal to kx q naught divided by x square plus r square to the power 3 by 2. I think this is the formula. Kx q naught divided by x square plus r square to the power 3 by 2. Okay, so that's the electric field, or x component is Ex, you can call it as this, right? Now, let us investigate some values, investigate the value of electric field at some specific points, right? At some specific points. So, starting with which specific point? Let's say at infinity. At infinity, electric field will be how much, guys? You are very far away from the that ring, very far away. You know, ring of course has got charge, like you can see here. No, it is charged. I've not drawn it here, but of course it is implied. It is charged like this, right? Now, what I was saying is that electric field will be how much? If at infinity, it will of course be zero. It will tend to zero, right? At infinity, it will tend to zero, right? So we know that it will be zero, somewhere zero at infinity. Now let's find at some other point also. Okay, we can fix that part, no? And then write everything around it and then keep shifting it and let it be there. That's gonna done. Right? Okay, let me try something. I just got an idea to make things better. I will save this as set as background, and it up. So this part is background. Now I can select things. Nice. And what if I make this also background? This also I'll make it a background object. Can I do that? Lock is there. Line thickness is there. Lock. Can I lock it? So if I move it around, only that will move. Very good. Now it's awesome. Okay, so writing part I can move, and this part I can keep it here, right? The diagram will always be there. So the diagram will always be, let me just think, guys. I'm just thinking about it, about a good idea to carry out my teaching. I will ensure this is here and fixed, and the diagram is there, and I can, the writing part can move on, the diagram will stay there. Brilliant, right? Absolutely brilliant. That's nothing like it. So just keep it there, and everything that's written there along with the diagram will stay there. What do you want will stay there, and you can move everything else around. That's a perfect plan, I suppose, right? Very good. Okay, so fine. So let me implement what I just thought. Lock it and lock it again. Buddy. That's logged and this is not logged. So I can play with this object. I can just copy it, right, and bring it here. Brilliant. Nice. And then I can move this around, and these equations will be can be moved around without having to move this. Right? Makes so much sense. Awesome. Alright, can I make this small also? Perfect. Fine guys. I discovered something great. That'll be of immense use for me in teaching. Now see, uh, if I want to find out the electric field at this point, right? So what will be the electric field at that point? Here x is how much? Here x equal to 0, right? So x equal to 0. If I put x equal to 0, I put x equal to 0 here, x equal to 0 here. So what does it turn out to be, guys? See, this numerator becomes 0, right? And there is something like I to the power 3, but that doesn't matter because your x is 0, dragging everything to 0. So electric field at x equal to 0 at the center is 0, right? Electric field is 0. So we found out that Ex at x equal to 0 equals to 0, right? You know, at the center electric field is 0. And at infinity, what is the electric field? That is also 0, right? That is going down to 0 as you going to infinity. Electric field is going down to 0, right? So I hope these two parts are clear to you, that electric field is 0. You know, both at infinity and at the center electric field is 0, right? So it starts from 0, ends at 0, but somewhere in between electric field will be there, right? It will be there. But here it is 0, here it is 0, somewhere it is there. So you understand the graph will be something like this. That means at one point it is going to be maximum, right? And that happens at x equal to a by root 2, where a is the radius of the ring, and x is equal to a by root 2, the electric field happens to be maximum, right? And actually we can do the calculation also. I can differentiate and show you, you see, but it will be a very lengthy process if I have to find out where it is maximum. So to find point of maxima, put differentiation of Ex divided by dx equal to 0. That's all you have to do, then it will get the point of maximum. But that's a very lengthy calculation, so I'm leaving that to you kids. If you have a problem, let me know. I can derive it in the next class. But as of now, That should suffice. Right? Okay, move ahead. Now let us find out the electric field at the center of the arc. Right? So I'll shift the diagram a bit. Electric field at the center of curvature of an arc. Okay. And now I'll fix it again. I'll lock it. What's the difference between lock and background? I'll lock it. Okay. So let us find out the electric field at this point. Okay. So how do you find out the electric field at this point? Due to a arc, and the total arc angle is how much? Theta. And before that, you have to tell me direction of electric field is found to be along what? So at C point, you want to find out the electric field will be how much due to a arc subtending an angle theta. What will be the direction of the electric field line? So for that, we will draw a line. We'll draw a vertical line, okay, like this. Like this. And electric field will be exactly along this line. Right? And how much it will be, let's try to find out. So for that, I will take a differential element here, dq, right? And we'll see what is the direction of electric field at this point due to that dq. So as Coulomb's law tells us, it will be along this line, right? Along this line. Okay. Like this. And it will be a small electric field, let's call it dE, right? And what will be the value? Kq means dq divided by distance square, which is r square, right? I hope that's clear to everybody, right? But now there's a problem with that. But that's fine, no problem as such, but we have to recognize something there. Now you will see that this angle is phi, right? Now which makes this angle also how much? Phi, right? Both the angles are phi. So I know that electric field is only going to be along this direction. That means I can say direction of electric field is found to be along what? Along the, what is this line, guys? This line is called what? It is called the ANGLE, angle bisector. Is it not? It's the angle bisector, right? So direction of electric field line is along the angle bisector. A dot B, angle bisector, right? Full form I've written there, angle bisector. That's where the electric field lines are, right? Along the angle bisector. Alright. And angle bisector here is vertical, right? Like there it is vertical, here also angle bisector is vertical. So that means this small electric field that we have drawn due to dq is not what is really going to be present eventually. What will be present? This will not be present. Its component, vertical component will be present, because that's why electric field is vertical. So its vertical component will be present. Right? Everything else will get cancelled. And let's find the vertical component. How much will it be? So that will be dE ka cos phi. That will be the vertical component, right? That is differential electric field in the vertical direction. DEV is coming out to be dE cos phi, right? Okay. So if you want to find out the total electric field, now we want to find out, right, what is the total electric field at that point. I have to find out the value, what is the electric field at that point. So how do I get it, guys? I take DEV and I add all such DEVs. So basically, if I have to write total electric field in the vertical direction is integration of DEV. I hope you understood that part. Integration of DEV. That's what is the total electric field, right? Integral DEV. Where DEV is dE cos phi, right? So let's put the values. Integral DEV, let's put the values. Integral, sorry? Integral DEV, which is equal to dE cos phi. Right? That will give me EV. EV means vertical electric field. That's you have to find out. That's the net electric field, right? Due to all such elements. Right? Integral DEV. Let's integrate it. For that, I need D. What is D, guys? Well, D is k dq by r square into D is k dq by r square into cos phi, you know. Right. Then what I can do is I can write dq as something like this is dq, no? What can I write? Dq is this charge, guys. This charge is dq, right? So dq can be written as what? Differential charge can be written as lambda times dl, right? lambda times dl, and dl is what? dl is this length. Not the best arc. Come on. No. Yeah, more like it. This is dl. This part is dl, right? Okay, that part is dl, guys. Is it clear till here? Hmm. So dq can be written as lambda times dl. Okay, what will be the relation? And also, don't you forget that this angle is how much, guys? This teeny tiny angle here, blue color. This angle is d phi, right? That angle is d phi. Hmm. Can you guys see it from here? The diagram is it clear? Okay, d phi. Hmm. Right now, I can write theta is equal to L upon R, right? So I can write d phi equals to L upon R. L is the arc length, which is like dl upon, sorry, dl upon R. I can write, you know. So from there, I get that dl is equal to what? R d phi. Right? And that value of dl, I can go and substitute here, and I'll get R d phi. Right? So dq is equal to lambda R d phi. That's what I'm getting. And calling it equation number 1. And I can write putting value of dq from equation number 1, right? Putting value of dq from equation number 1 in equation number 2. Let's call this equation number 2, right? And that should give me the value of EV. Let's find out. And before I go do that, let me lock all of this. I will lock this entire thing as well. Lock it. That's locked up. And what is locked up? Let's see. This is also locked up. This part should have got locked up, but fine. And this entire thing should also be locked up. You don't want this to move. Lock it up. Come on, lock it. Right. So now when I move, everything will get moved except that part. I don't know why that got locked. I didn't lock you, damn it. Why did you get locked? You open up. Right. That's unlocked. Now I can move things around. You see, the derivation can be moved around. And what about this entire thing? They are also locked. They're not set as background. Right. Yeah, makes sense. Okay, that angle bisector should also be logged. No, it's fine. Fine. So we have done the derivation till here, right? Let's go ahead from here. Putting value of dq from equation number 1 and 2. So what do we get, guys? If I do that, I'm putting in 2. So EV comes out to be what? Integral k into dq. But what is the value of dq? It is lambda r d phi, right, into cos phi whole divided by r square, and r gets cancelled. And k, lambda and r are constants, they can move out. It will be like k lambda by r into cos phi d phi integration, right? And then phi varies from where to where. So what is the minimum value of phi? If you see at this point, phi is how much, guys? Phi initial, you can say it is minus theta by 2. And at this point, you can say that phi final is plus theta by 2. And here it is minus theta by 2, here it is plus theta by 2, right? Phi has got two different values, initial and final. Right? And that's what we'll integrate it from initial to final. And cos phi integration is what? What is cos phi integration? K lambda by r. Cos phi integration is sin phi, right? From initial to final. And then you can put in the values, and that will give you K lambda by r sine of uh, final value, which is how much? Final value is theta by 2 minus sine of initial value, which is minus theta by 2. Right. And that will come out to be 2k lambda upon r into sine of theta by 2. Right. That's it. That's the answer. That's what you have there, right? When you put the value of k, you'll get that result. You'll get this is the electric field. Right? Take it off. Let's go ahead and let's find out the force. So what they're saying is that there's a ring, it is charged, of course, it has got some charge, right? And this will apply an electric field at that point, right? There will be some E, whose value we have just found out. How much was it? It's 2k lambda upon r, what was it? 2k lambda upon r into sine of theta by 2. And theta is how much, guys? Theta will be this full angle. You can see here, with theta we have to take full angle, right? Full angle we have to take here, full angle. So here also full angle means 180 degree. So it will be sine of 180 upon 2, which is sine 90. So electric field we have got is how much? 2k lambda upon r. Sine 90 is 1. 2k lambda upon r. That's electric field. Now, what will this electric field do? It will apply a force on this point, right? This poor fellow will experience a force, right? It will experience a force, and force will also be in this direction. Force is equal to charge into electric field. We have seen the formula before, right? So you have to find the force required to keep the charge stationary. So F is equal to QE is the force acting on the charge due to the ring. So you have to apply the same force to keep it stationary also, right? Same magnitude of force. Not same force, same magnitude of force. And how to find that magnitude? What do we have to do? Q into E you have to do, Q into E. And E is how much? 2k lambda upon R. Right? That value of E you can substitute here. And you'll get the answer. Which option are you getting? Getting the first option. Copy it. Let's go ahead. Let's do this question. How many do we have? Okay. You have to find the magnitude of the electric field at O point. At O point, you find the magnitude of the electric field and the direction also. Okay. So let's see how do we do this part. Magnitude and direction of electric field you have to find. That's it. It seems to be easy, a simple problem. Let's see. Oh, so electric field at point O. You know, how do you do that? So we see that there are two types of charges here. One is negative charge, because of which the electric field will be along the angle bisector, like this. And the direction of the electric field will be along this line. I'm not able to select here. Okay. Electric field will be along this line, this direction, right? Since it's a negative charge, the electric field will be towards this, right? What is wrong with this? Why is it getting selected? Is it good? Why is it going? What's the problem? I'm not able to draw a straight line or what? What is the problem? What? It's not working. What's wrong with it? Huh? What's wrong with this? And positive charge electric field will be, let's see in which direction. It will be away from it, right? somewhere in this direction. You know, this is E blue or E positive rather. Right? E due to positive. And how much is the value, guys? Due to the positive charge. For that, you have to find out the angle theta. How much is this theta? This angle is 90 degree, right? E plus will become how much? You know the formula is 2k lambda upon r into sine of 90 by 2, which is sine 45, right? So it becomes 2k lambda sine 45 is 1 by root 2, and that's root 2 k lambda upon r. Right? That is E plus, and let's call it E, right? And let's find E minus. That will be 2k lambda by r into sine of 92 by 2. Sine 90 by 2 is 1 by root 2. That makes it 1 by root 2 k lambda upon r. We'll call this also E. So both are E basically, right? That's E plus and this is E minus. But E plus and E minus are both equal. You can see both magnitudes are equal. Root 2 k lambda by r, common magnitude, right? And you wanted the net electric field will be in which direction, right? So let's find that out. Net electric field will be in which direction? And of course, for that we have to drop the we can use parallelogram law, and it will be somewhere here. So here is the resultant electric field, E resultant, right? It's in this direction. And the value of E resultant will be how much? E resultant will be under root of E square plus E square plus 2 times E1 E2. So we are using this formula, no? You know resultant formula is what? Root of E1 square plus E2 square plus 2 E1 E2 cos of theta. What is the angle between them? 90 degree. Right? So that will come out to be, and E1 E2 are both equal. They're both equal to how much? E square plus E square plus 2 E square cos 90 is 0. Right? So you'll basically get equal to root 2E. That is the resultant electric field, root 2E. Right. So this is our resultant electric field. ER equal to this root 2E. Yeah. And if you plug in the value, how much is coming out to be? E resultant is, and first of all, it is coming in which direction? The left direction, right? So which option is correct? Minus I cap. That one thing is clear. Then the value is root 2E. Value means magnitude. And E is how much further? Root 2 k lambda by r. So the answer is 2k lambda by r. So that's the uh, magnitude of the electric field. Got it? So you can take this down. No? That will be all. So next time we will go to plot Ex versus X. We already done that, right? I don't know why it's coming. We already done this. Plot Ex versus X. We've done this part. We'll do this question and then this question, and then we'll go to direction of electric field lines. Kind of.